Now we'll map out a constant temperature process in PVT space. I'm going to operate under the assumption that you already watched the tutorial on a constant pressure process in PVT space. That means I can gloss over some of these details. It has a lot in common with that process, except now we're holding the temperature constant instead of the pressure. So here are our three template plots for a TV plot, a PV plot, and a PT plot, and we'll draw the piston as it moves. Our initial state is again going to be a liquid, so we'll put it in the TV, PV, and PT plots, and I'll even note it under the piston that we're in a liquid phase initially. Let's start evolving the system. So we start expanding the piston barely. It's still liquid, so still mostly incompressible. It's horizontal motion on the TV plot and vertical motion on the PT plot. Both of those make sense because we fixed the temperature to be constant. The only one with an interesting slope is on the PV plot, where we can see it's now sloped down and to the right. That's because we have to lower the pressure if we fix the temperature and we're allowing the liquid to expand, as you can see from the fact that the specific volume increases for a closed system. Once we reach the side of the vapor dome, once again we're in the saturated liquid phase. That's the state that we've labeled F. Now we'll start crossing the vapor dome again. Alright, so we cross the vapor dome, the piston continues to expand. That means that temporarily we're in a two-phase liquid-vapor mixture until we reach state G. G is on the right side of the vapor dome, just as it was in the constant pressure case. You'll see some similarities. The PT plot hasn't changed at all as we've crossed the vapor dome, just as it did not change in the case of constant pressure process. That makes sense, it's exactly the same phenomenon. In the TV plot, we had to have a horizontal line because we fixed the temperature to be constant. That makes sense. In the PV plot, we have a horizontal line in pressure. Well, again, that's very similar to what we got when we fixed the pressure. When you're crossing the vapor dome, if you fixed one of the two, pressure or temperature, the other one also has to be fixed. We saw that in the other case of a constant pressure process. We see that for a constant temperature process as well. Now we've reached state G, where we're on the other side of the vapor dome. This is what is called a saturated vapor, meaning that it is 100% vapor, but it's very near the transition region, namely the vapor dome. Now let's continue evolving our system at constant temperature. As we expand the piston further, now we can see that we're transitioning completely into a vapor phase. We're not saturated anymore. That corresponds to horizontal motion on the TV plot, vertical motion on the PT plot, and now we've moved sort of down and to the right on the PV plot. That is still a superheated vapor. If you think about it, it's at a higher temperature than it would be if we had been operating at constant pressure for this case, crossing the vapor dome. But otherwise, it really has a lot in common with the constant pressure process. So once again, you want to become accustomed to drawing these characteristic curves. They will help us to evaluate systems quantitatively when we reach that point.